Welcome to our talk on TxT, cross-modal end-to-end learning with transformers. I'm Jan-Martin Steitz, and this is a joint work with Jonas Pfeiffer, Iryna Gurevych, and Stefan Roth from TU Darmstadt and Hessian AI. There is a rising interest in multimodal reasoning with tasks such as visual question answering or short VQA. This allows for actively querying image data for visual information based on natural language. In this work, we experiment with the VQA version 2 dataset in particular. Multimodal pipelines for VQA typically rely on visual features from the popular faster RCNN object detector pre-trained on visual genome. The image region features and their respective bounding box coordinates are pre-extracted to be used later in conjunction with the language model. Thus, they are fixed and can't be tuned to the multimodal task at hand. Most recent language models leverage the omnipresent transformer architecture and are trained as encoders predominantly with masked language modeling objectives. Multimodal learning is then achieved by combining textual and visual representations to learn a shared multimodal space, in our case to solve a visual question answering task. In this work, we aim to devise a unified architecture for multimodal reasoning where the visual and textual pipelines are tightly integrated and can be trained end-to-end. But as faster RCNN makes heavy use of subsampling to balance data during training and needs non-maximum suppression, it is not easily integrated into a multimodal end-to-end pipeline. Transformer-based models recently showed benefits also for computer vision tasks. One example is the detection transformer, or DETR in short, a model for object detection. It has a conceptually simple structure compared to faster RCNN. It uses a CNN backbone to extract a feature map, which gets passed to a transformer-based encoder-decoder structure for predicting objects. DETR treats the detection task as a direct set prediction problem by querying the encoded feature map with a fixed set of learned queries. DETR does not need any form of non-maximum suppression. It is thus fully end-to-end trainable and a good candidate to combine into a multimodal model. Additionally, we use Deformable-DETR, which is a multi-scale version of DETR based on deformable attention. For that, multiple feature maps of different scales are extracted from the CNN backbone. Deformable-DETR needs only a tenth of the training rounds of DETR and improves over DETR for smaller objects. As the full multi-scale version is computationally heavy at test time, we developed a scaling method. We query with only one of the feature maps in the first self-attention of the encoder, which produces a single-scale output that still encodes multi-scale information. All following layers then work on single-scale feature maps, which is faster. Selecting different feature maps for the query allows to control the trade-off between computational speed and average precision of the model. We chose the feature map with a stride of 16, maintaining comparable inference speed and average precision to DETR but with faster training time. Our multimodal end-to-end trainable model, called TxT, employs DETR or Deformable-DETR as object detector. The predictions of the object detector get directly passed to the language model at runtime. The object features and coordinates are projected to the dimensions of the language model and combined. They are used alongside the text embeddings, so the language model can learn to reason over its multimodal inputs. Our model enables fine-tuning both language and visual components on the downstream task in a fully end-to-end manner. Before we can bring together transformer architectures for object detection and language modeling, we first need to assess whether transformer-based detectors yield a competitive baseline. To that end, we use pre-extracted features from the object detectors for a visual question answering task. DETR and Deformable-DETR encode the semantic information in a single feature vector for each query in the transformer-based decoder. We posit that this leads to learning more object-specific information and global scene context not being captured. As this global scene context is arguably important for VQA and other cross-modal tasks, we compensate for the loss in global context by augmenting each output feature vector with context information from global average pooling of the encoder output. This leads to a gain of 1.3% in VQA accuracy. Also note that adding the same contextual information to faster RCNN features in contrast does not aid VQA accuracy. Even though Deformable-DETR is in principle a stronger detector than DETR, in the VQA context it does not perform as well out of the box. To understand this, we take a closer look at the influence of the loss function. DETR is trained with a cross-entropy loss like faster RCNN, but Deformable-DETR uses a focal loss to improve on hard-to-detect objects. If we compare the distribution of the number of extracted objects per image between faster RCNN and DETR, they are roughly similar. But for Deformable-DETR trained with a focal loss, the distribution changes drastically. We then train Deformable-DETR also with the cross-entropy loss to regain a faster RCNN-like distribution. In a first experiment, we investigate if DETR and Deformable-DETR are able to produce object feature descriptors whose representational power for visual question answering tasks is comparable to the widely used faster RCNN. We assess this through the VQA accuracy. We pre-train DETR and Deformable-DETR on visual genome similar to the faster RCNN used by Anderson et al. The results show that both DETR and Deformable-DETR are competitive, especially considering their low dimensionality of 512, including the global context, compared to 2048 dimensions of faster RCNN features. Also, these results are achieved with only ResNet 50 backbone compared to ResNet 101 for faster RCNN. We then train the text model on VQA. As with the pre-extracted features, we threshold the object predictions by confidence such that DETR produces a mean of 30 objects per image, like faster RCNN. During the course of the training, DETR learns to predict more boxes above the threshold, saturating at around 80. The thresholded text model improves by around 0.3% over pre-extracted faster RCNN features and 1.5% over pre-extracted DETR features. Next, we use all predicted objects of DETR and Deformable-DETR for the multimodal part of the model. We note that part of the improvement over faster RCNN features stems from the full set of object representations, but tuning the object detectors to the VQA task further improves the accuracy. Text with Deformable-DETR reaches 69.06% VQA accuracy, around 0.3% above the faster RCNN baseline, and text in combination with DETR reaches 69.93% VQA accuracy, around 1.1% above baseline. In this work, we integrated detection transformers as object detectors into multimodal pipelines. We showed the importance of global context and a suitable loss function for that task. Further, we suggested a speed-up mechanism for the multi-scale detention of Deformable-DETR. Finally, we proposed our text model, an end-to-end trainable transformer-based pipeline for cross-modal reasoning, and showed its benefits on the VQA task. Thank you for watching.